Good morning, everyone. Hope everyone is doing good today. So our plan is to continue on with our description of permutations and how to work with them through their algebra, so multiplication or composition as we called it. And then we're going to look at properties. So I'm just going to preface this with saying we're going to, our array form of a permutation, which I've written down here. For example, this alpha is written in array form. We're going to only be using this form for the duration of this lecture, and then on Monday we're going to look at a more compact form. So if you're worried that as soon as our permutations start getting bigger, that there's going to be a lot of writing, the answer is going to be, well, no, there's not going to be that much writing. We're going to look at a more compact form representing our permutations. And on the same note, you're probably noticing that when we do these calculations, we're doing multiplications, and then we'll eventually get into inverses and calculating inverses. Maybe I'll back up to the example that we were on, just so there's the example we were on last day, and we'll finish it off. We're going to be looking at calculating inverses and whatnot. But the main idea is, yes, there'll be some aspects where we're going to have to compute things or calculate things, but I want you to think sort of more big picture. Our goal is to come up with observations, to come up with some ideas about how permutations are behaving under multiplication, so that we can be smart and only compute things when we have to compute them, and not when we can appeal to some sort of general result that holds. And this example here is starting to illustrate that. So as we're going through this, I want you to just keep in mind that calculation is one thing, and we sort of do it as a last resort, but our goal is to hopefully be a little bit smarter in how we do these calculations. So as a sort of analogy with, elementary school mathematics, you may be asked the question, if you have 14 and you multiply by 23, is the answer even or odd? And if you're an elementary school student, you would probably actually do the calculation, 14 times 23, and get a big number, and then look at the last digit and say, is that last digit 0, 2, 4, or 8? If it is, then it's even. If it's not, then it's odd. But can we answer that question without calculating? And the answer is yes. We have 14, that's even. Any even number times any other number is always going to be an even number. So I don't even have to multiply 14 to 23 to know that the answer is going to be even. That's the kind of thinking that we want to have moving forward. We want to avoid calculation when we can, and only do it really as a last resort. Okay. Let's continue on with these examples. So alpha to the power of 4. We talked about this at the end of last day. We could write alpha times alpha times alpha times alpha 4 times, and then do the whole trace through all the 4 arrays and see what comes out. Or we can start to be a little bit smarter in how we do this, and we could say, well, I've already worked out alpha cubed. I just did it in the last line. So I could work out alpha cubed times alpha, and that's just a multiplication of 2 permutations. Or, as someone observed in the chat, that this is also just alpha squared times alpha squared. And that might be even easier to work out, because that's just the same permutation multiplied to itself. So we might as well do that one to see what it works out to be. So this is 1, 5, 3, 2, 4. 1, 2, 3, 4, 5. 1, 5, 3, 2, 4. So there's alpha squared written out twice. See if I can squeeze it in there next to where I wrote some stuff at the end of last day. And now we're going to go ahead and do the product of alpha squared with itself. So 1 goes to 1, and then 1 goes to 1. So 1 goes to ultimately 1. Remember how we're doing this. 2 goes to, I'll just a refresher. I want to know what 2 goes to. So I'm looking at the far right and saying, okay, what does 2 go to? Well, I look back at my product and I say, well, the first permutation takes it to 5. So 5 comes out of that one and then goes into the next one, and then 4 comes out. So that means 2 ultimately ends up at 4. And that's what we're doing, and we'll do these things in our head. This is probably going to be the last time I do the trace through diagram in class, because I'm going to talk our way through it. So 3 goes to 3, which goes to 3. 4 goes to 2, then 2 goes to 5, so 4 ends up at 5. 5 goes to 4, and 4 goes to 2, so 5 ends up at 2. And as a double check, I want to make sure all of the numbers in that second row of my result, they are all distinct, and they are all numbers 1 through 5. And that's a good check, because if I've got any numbers repeating, I know I've made an error somewhere, because this result has to be a permutation. So those numbers have to be the second row has to be a rearrangement of the top row. How about alpha to the 5? Well, that we could do alpha to the 4 times alpha, or we could do it alpha cubed times alpha squared. However we want to do it. I don't even know if I have alpha written down. And it's way back there. So since alpha is way back there, it's not even in my sight, I'm going to do it alpha cubed times alpha squared, because both of those I can see on my page in front of me. So let's do an alpha cubed. 1, 2, 3, 4, 5. 3, 2, 1, 4, 5. And an alpha squared. 1, 2, 3, 4, 5. 1, 5, 3, 2, 4. And we get our result of 1 goes to 3, which goes to 3. 2 goes to 2, which goes to 5. 3 goes to 1, which goes to 1. 4 goes to 4, which goes to 2. 5 goes to 5, which goes to 4. And so there's our product. That, talking to yourself as you do it, I do it out loud because I want you to hear what's going on in my head, but that's every time I do a multiplication and permutations, that's my inner monologue. That's my inner discussion with myself. I just verbally state out what's being traced to what and how it happens as I go along. Okay, so alpha to the 6. We can notice that this is alpha cubed times alpha cubed. And this is where that text comes in way back here, which we talked about at the end of last day. This alpha cubed just swaps 1 and 3. It doesn't do anything to 2, 4, and 5. So if we swap 1 and 3, and then we do it again, we end up swapping them back. So this is going to be the identity. And so we get that result. Now this is what I mean by avoiding calculations when we can. Notice that I didn't do alpha to the 6 by actually writing down alpha 6 times, nor did I do it by taking alpha to the 5 times alpha, or alpha to the 4 times alpha squared. I did it by alpha cubed times alpha cubed, because if I look back at alpha cubed, I notice that that's just a swap of 2 objects. And so doing it twice swaps them back. And so this is what I mean by calculating without calculating. We're being a little bit smarter in how we do our work. Avoid calculations if we can by appealing to some bigger results. And we'll start to generate results as we go along that allow us to do these things more frequently. Okay, so let's go through the next bit. We're still uncovering properties of multiplication. And so if we're uncovering properties of multiplication, we're going to still do a few more of them. In this case, I've got alpha and beta written out here, and I want to compute the product, alpha beta. So let's go ahead and compute the product. 1, 2, 3, 4, 5. 1 goes to 3, which goes to 4. 2 goes to 4, which goes to 1. 3 goes to 1, which goes to 5. 4 goes to 5, which goes to 2. 5 goes to 2, which goes to 3. So there's our product. What about the next one? 1, 2, 3, 4, 5. 1 goes to 5, which goes to 2. At this point, I already know something. What do I know? If we were ever wondering, does it matter which way we multiply permutations, whether I take alpha first or beta first, what do I know right at this moment? Does it matter? Does order matter? Yeah, order matters because these are different. This one takes 1 to 4, whereas this one takes 1 to 2. And that's all I need to know in order to know two permutations are different from each other. If they just behave differently on one input, then I know they're different. Okay, so that's just something to keep in mind as well, that if you want to know two permutations are different, you only need to show they act differently on one input value. And that tells you that they are different as permutations. Okay, so let's continue on with the calculation. 2 goes to 3, which goes to 1. 3 goes to 4, which goes to 5. 4 to 1, which goes to 3. 5 goes to 2, which goes to 4. And the thing we've just observed was that these are equal and not equal to each other. And so what this means is that permutation multiplication or composition, I'll refer to them either way, but maybe I'll call them multiplications or products. The order in which you multiply permutations matters. If two permutations, say sigma and gamma, if it doesn't matter which order you multiply them in, sigma times gamma equals gamma times sigma, then we say that those two permutations commute with each other. In general, though, we have that permutations don't commute. It's a very special case when they do commute with each other. Most often, they do not commute with each other. We will actually come up with a characterization as to when they don't commute with each other, and we'll be able to characterize these things in the next chapter when we have a slightly better notation for dealing with permutations. Yeah, that's a good observation. When they are inverses of each other, they will commute. Yep, if you multiply a permutation to its inverse, it doesn't matter which side you multiply the inverse to. It's always going to be equal to the identity, and so they will commute. There's also another way that they would commute. Let's just say one of the permutations swaps 1 and 2, and the other permutation swaps 3 and 4. Then it doesn't matter which order you do it in. Swapping 1 and 2, swapping 3 and 4. I could swap 1, 2 first and then 3, 4, or I could swap 3, 4 first and then 1 and 2. So in some sense, when the two permutations are acting on different collections of objects, they will commute with each other. It doesn't matter which order you perform them in. Right, like two people playing, or a group of people playing musical chairs in one room and a group of people playing musical chairs in another room, they have no influence on each other. That's sort of the idea here, was what as to why they will commute. There's sort of two different sort of permutations going on, and it doesn't matter whether you do this one first or this one first. It's only really when they have something in common that you're going to run into issues where they don't commute. But that's just something to be aware of. So when we're doing algebra, when we're trying to uncover things, this is the key thing. I'm not able to just go, oh, I'll switch their order, because you can't switch their order. We'll run into troubles. Much like matrices in linear algebra, it matters which order you multiply them in. So won't both just be the same array with rows swapped? Or are we talking inverses? Karen, is that? Yeah, you got it. Yep, exactly. To get an inverse, it's really just, as you said, it's just swapping the two rows in the array, flipping the top and the bottom row. And that's what we'll see here. So given a permutation, can we find a permutation beta such that alpha beta is equal to beta alpha is equal to the identity? In other words, can we find a permutation that undoes what the permutation alpha does? And the answer is yes. And this is because since permutations are bijective, they have inverses. Right. This is really just a property of the fact that they are functions, they are bijections, and so they have to have inverses. That's sort of the higher level view as to why these inverses exist. But it's all right if you're struggling to see why bijectiveness implies they have inverses. We'll just see immediately why permutations, in our case, have inverses. So if I consider alpha, 1 goes to 4, 2, 5, 3, 1, 4 goes to 3, and 5 goes to 2. And I want to find a permutation that undoes what alpha does, then what I need to do is, if this is alpha here, then I need to find a permutation beta that just undoes it. So alpha scrambles these things in some way. Beta is supposed to undo that. So all we do is just make sure beta restores everything. So I just take these arrows and put them back where they should be. So maybe 1 goes off to 4. Well, that means 4 better come back to 1. 2 goes off to 5. So 5 better come back to 2. 3 goes to 1. So 1 better go to 3. 4 goes to 3. So that better come back to 4. And 5 goes to, I'm going to actually move this one a little bit closer here and then drop it down. Just try to get the same image of as above. So it's just a mirror image. It's like a reflection along the middle line that goes through these things, that we can work out what beta is in order for it to unscramble it, so that the composition of alpha followed by beta is just the identity. In other words, 1 goes to 1, 2 goes to 2, and so on. To actually write down what beta is, we can do that now, because I can read beta off from my diagram. 1 goes to 3, 2 goes to 5, 3 goes to 4, 4 goes to 1, and 5 goes to 2. And so that's the beta permutation, which undoes alpha, or the inverse of alpha. And as Karen pointed out in the chat, that it actually is quite straightforward to get beta. All we have to do is, let's just look at this. What I will do is I will flip it over. I will flip alpha over. And when I flip alpha over, 1, 2, 3, 4, 5, then, so just flip it over, and that is beta. Typically we write the array form with the input in numerical order on the top row, but it's the scrambled order in the top row, but that doesn't matter. We still have this input output relationship. So 1 goes to 3, and that's what beta has. 2 goes to 5, that's beta. 3 goes to 4, that's beta. So beta is just obtained by flipping alpha over and then rearranging the rows so that the inputs are in numerical order, so they're more easily seen. Yep, you could just swap the rows and make it look how you want. That'll give you the input. And oh, swap the columns. Yeah, exactly. At this point, you can then swap the columns, and you could just say that's 1, 3, 2, 5, 3, 4, 4, 1, 5, 2. So that's equal to that one, because all it's encoding is an input-output relationship, and that input-output is just obtained by reading columns. So you can reorder columns as long as you reorder the top and the bottom columns at the same time. You can reorder, top entries and the bottom entries at the same time. In other words, you can swap all the columns and reorder it in any way. That gives you the same permutation. So here's the cool thing. That's computing inverses. If you think about any other class where you've computed inverses, linear algebra, there was a lot of work involved in computing the inverse of a matrix. Computing the inverses of functions in pre-calculus or calculus, there was a lot of work involved here. But for permutations, inverses, they're quite straightforward to work out. Just flip them upside down. Yeah, exactly. It's like f of x equals y is going to f of y equals x. You got it. Yeah, so that's the key thing, is inverses here, very nice and straightforward to work out, because all we're doing is, in some sense, we're just reversing the arrows. We're reversing the arrows in our arrow diagram. So for permutations, there exists a unique permutation, for permutation alpha, there exists a unique one beta, which is its inverse, such so that by definition that means it's alpha beta is the identity, and so is beta alpha. We call it the inverse, and we use this notation. Beta can be written as alpha with the superscript of -1. So we still use that inverse notation. So how do we find inverses? We've already seen that this is a fairly straightforward task. We could just flip the array form over, or in terms of the arrow diagram, we just flip the arrow diagram upside down. So I just follow the arrows in the reverse order. So if I'm thinking about where should 1 go to, well, I look at the bottom row, find 1, and reverse the arrow. 1 goes back up to 3, so 1 goes to 3. 2 went to 5. I like to read it like this. So 2 went to 5. That means 5 has to come back to 2. 3 went to 1, so 1 comes to 3. Oops, I didn't do oh yeah, that's fine. 1 comes to 3, and then what about the next one? 1 went to 4, so 4 comes, oh, just a minute. What did I do here? 1 goes to 3 and 3 goes, yeah, okay, so 4 goes, there we go. 4 goes to 1 because I'm just reversing the arrow. And then what about the next one? What went to 2? 5 went to 2, so 2 goes to 5. And 4 went to 3, so 3's got to go to 4. So we just reverse all of the arrows. In some sense, you just flip the diagram upside down. Same with for the array form, 1, 2, 3, 4, 5. I'd start at the bottom row now, and then just read off the top row. So 1 in the bottom row goes to 3, 2 in the bottom row goes to 5, 3 in the bottom row goes to 4, 4 in the bottom row goes to 1, 5 in the bottom row goes to 2. So there's our inverse. We will actually find a simple or as straightforward as it is to compute inverses in these forms. We're actually going to find that in our form that we introduce for representing permutations in the next lecture on Monday, that it's even easier to write down inverses. We're going to find an even simpler way to do that. And again, it's just reversing the order in which we write numbers. So computing inverses is merely just a matter of reversing whatever object is that you're doing. So here's another example, find the inverse of this beta. So again, I like to start in the second row and just read up. So 1 goes to 5, 2 to 3, 3 in the second row goes to 1 in the top row, 4 in the second row goes to 6, 5 in the second row goes to 8, 6 in the second row goes to 7, 7 in the second row goes to 2, and 8 in the second row goes to 4. And so then we could check, once we've got these values, that we actually did get the right inverse, and that is just by reading it across. 1 goes to 3, and then 3 goes to 1. And that's really just the way we define the inverse. We just made sure it undid whatever the first one did. So if 1 goes to 3, then no surprise that 3 is going to go to 1, because that's all we did to create the second matrix, or the second inverse, or the second permutation, was to reverse whatever the first one did. So you can check that all values. 2 goes to 7, 7 goes to 2. 3 goes to 2, which goes to 3. So 3 goes to 3, and so on all the way to cross. Okay, so we get the identity there. So that's inverses. Now, what about if we had a product of 2 permutations and we want to compute the inverse of the product? So we could compute the product first, find that permutation, and then compute the inverse of that result. Alternatively, we could get the inverse by multiplying 2 permutations, namely the inverses of the 2 original permutations. But we have to be careful here in that the order is reversed. So if it's alpha multiplied by beta, and we're going to take the inverse. The inverse is beta inverse multiplied by alpha inverse. And the way I like to think about this is we're thinking actions. So you're going to leave the house in the morning. Let alpha be putting on your socks and beta be putting on your shoes. So you put on your socks, then you put on your shoes. You leave the door, you come back in the evening, and you got to undo that process now. What are you going to do to undo it? Well, you're not going to take your socks off first because they're trapped underneath your shoes. So you got to reverse, not only undo the actions you did in the morning, but you got to do them in the opposite order. So alpha followed by beta. If you want to undo that, you got to undo the second thing first before you can undo the first thing. So it's beta inverse followed by alpha inverse. And now we can check. You know, what does it mean to check? It means that I'm claiming that the inverse of this thing is equal to beta inverse alpha inverse. So, excuse me. So I'm just going to get rid of this for a second and say what I'm really interested in is this permutation, whatever it is, it has to multiply to alpha beta to produce the identity. That's what it means to be the inverse of it. So if that permutation, beta inverse, alpha inverse, multiplies to alpha beta to produce the identity, then it's its inverse. And now you can see why the order had to be reversed, right? I'm not allowed to change the order in which permutations get multiplied. Whatever order they're in is how I have to multiply them. I'm allowed to remove grouping brackets, though. So I can remove the grouping brackets because of associativity. And now at this stage, I can say, oh, well, I could multiply those two first. And that gives me the identity. Oops, I missed the inverse on that first beta. So that gives me the identity. But then the identity times any permutation is just the permutation itself. And then that's the product of two inverses. And that gives me the identity. So that means that it is the inverse. And you can do it in the opposite order as well. We could do alpha beta times beta inverse alpha inverse to see that we get the same result. This is the identity again. So that's alpha identity, alpha inverse, or alpha alpha inverse, or the identity. Okay, so that's another way to justify why the order had to be reversed. So that when you multiply alpha beta to this object we're claiming is the inverse, that the beta and the beta inverses match up with one another, that they're being multiplied together, or the alpha and the alpha inverse are being matched up with one another to be multiplied together. However, I like to think about the socks and shoes analogy much more, that in order to, if I do two actions to undo them, I have to do them in the reverse order and then undo each one of them in turn. In general, if I have a product of a bunch of permutations, alpha 1 through alpha k, and I want to compute the inverse, I compute the inverses of each one of them and then multiply them in reverse order. And that's what this last statement here says about in general. The inverse of alpha 1 through alpha k inverse is alpha k inverse, alpha k minus 1 inverse, and so on, delta alpha 1 inverse. Okay, so those are our properties of inverses. Now we know how to compute an inverse, and we have some basic properties of inverses that we can use. So Karen, why general? General in the sense that for more than one permutation in product, or more than two, I should say, because we're computing a product. So more than two permutations in product. So I mean by a general number of permutations. So we've got the result for two permutations being multiplied together, but in general for any number of permutations being multiplied together, the inverses are worked out in this way. Cancellation property. So this is starting to step us in the direction of we can do algebra with permutations. Now these things we're developing, they're the power tools we have for working with permutations. If you've done any courses before, it could be a stats course or MATCOM 201 or even some high school classes where you talked about combinations and permutations and counting rearrangements and things like that. Permutations were always just rearrangements of objects, and you were talking about counting them. But now we're taking a more sophisticated view. We're thinking of permutations as actions, and actions that can be combined with each other. And now we can start to do, and then actions that have inverses. And so now we're building up an algebra of actions. And with this algebra, we're going to start being able to work with equations and do what we would normally do in algebra. Manipulate symbols to get new expressions and things like that. And solve problems, most importantly. And that's what we're going to do. We're going to solve problems related to puzzles. So what are our cancellation properties? Well, the first one is if I have a permutation alpha multiplied by beta, and that actually turns out to be the same as a permutation alpha multiplied by gamma, then it means that beta and gamma had to be the same thing. So let's prove that. So I start with alpha beta, and I know that that's equal to alpha gamma. So that's the first thing I know. Now, what can I do? Well, what I can do is I can multiply both sides of the equation by alpha inverse. Okay, I'm going to move this slightly over so I have a little bit of room to write on the other side. And now I'm just going to do a bit of record keeping as to why each of these steps I'm allowed to do. So that first equation, alpha beta equals alpha gamma, that's what's given to us. That's our known equation. How did I get the second equation? Well, what I used was inverses exist. All right, I used the fact that alpha is a permutation, it has an inverse, so I know alpha inverse exists, and I can multiply it to both sides. If the two things I start with are equal, then when I do the same thing to both of them, the result will be equal. So that's why I have equality there, but I needed to know that I had an alpha inverse to multiply in the first place, and that's because alpha inverse exists. Now, what's next? Well, what's next is I can rearrange which multiplication I do first. This is the associative property. That's the associative property of multiplication. Is I phrased it as we don't need grouping brackets because it doesn't matter which ones you multiply first, as long as you don't rearrange the order in which they appear, but you can multiply any pair first and then go on from there. And this gives me the identity and the identity. And that's because alpha inverse alpha is equal to the identity. That's the property of inverses. So what I'll call this is I'll call this property of inverse. And then lastly, we get beta is equal to gamma, and that's because of the property of the identity. That's the whole thing about what the identity does. It doesn't do anything when you multiply by it. And so there is our proof of left cancellation. Put a little box down there, a little empty box indicating that's the end of proof, or if you so like, a little QED, any one of those to distinguish the fact that I have finished now the proof of my left cancellation property. The right cancellation is the same thing. It's just you're going to multiply by the inverse on the right. So I've made a record of the properties of permutations that I've been using at each step. It is helpful if you're doing arguments like this for you to keep a record of what the properties are you're using at each step, just to instill in your own mind that there are, so some of these things which when we developed them may have seemed obvious, like property of the inverse. You're like, yeah, that makes sense. It seems kind of obvious. I don't need to really write down that the inverse multiplied by another permutation just leaves it untouched or unaffected. But here's where I want you to see that we do use it to prove other results. And so it's important keeping that in mind as we're building up our algebra. Okay, so then we can do things like if someone says, oh, if you take your Rubik's Cube and you do a right hand, so a right twist of the right face, a twist of the up face, and then a counterclockwise twist of the front face, you get the same thing as doing 3 twists of the right face in the clockwise direction, and then a 3 twists of the front face in the clockwise direction. And you might be thinking, oh, I don't have a cube on me to actually verify this. Does that actually, yeah, maybe that, no, that doesn't seem right because the up face is moving, but the other one doesn't. So we can answer this question by just using cancellation properties. We could say, what I'm interested in is knowing if this is equal, so I'll put a question mark there, is equal to this. And we could say, well, there's a right twist that happens at the start of each one of them. So I can get rid of it. So I can replace it with this, r squared f3. And that's because I used left cancellation. I canceled the r off of the left of both of them. And then for the next one, I could say, well, a front face twist of 1 click counterclockwise. Let's see, so we got a front face, and I'll try to get this because I think my camera's being reversed. So counterclockwise, 1 click. That's the same, so counterclockwise 1 click ends up with the yellow coming over here. That's the same as doing 3 twists in the clockwise direction. So those are the same. So what I could do is I could say, well, that's the same as u f3. And so it's a question of, are these two the same? Ah, but now I can do right cancellation, because I have an f cubed on the right of both sides. So by right cancellation. And at this point, we can say, okay, yeah, I don't believe this. Because this is telling me that if I twist the right face twice, that's equivalent to twisting the up face. So if I twist the right face, let's see which is right for you. This will be right for you. If I twist the right face twice, that's the same as twisting the up face. No, definitely they're not the same. So u is not equal to r squared, and therefore r u f inverse is not the same as r cubed f cubed. Because if they were the same, then we've just shown that u has to be the same as r squared. So this is sort of an example in the context of the Rubik's Cube is how these cancellation properties and algebra can work. So now we're doing algebra to answer questions about what's going on with the cube. Okay, so now I'm just going to summarize everything that we've developed so far. If I've got a permutation on n objects, then we can look at all possible permutations on n objects. All possible permutations on n objects. If I collect those together and put them in a set, so I take all the permutations, I put them in a bag, and now this is my bag of all possible permutations. That set is what we call the symmetric group, S sub n. And we know various things about them. We know that the symmetric group, so just how I define it there, is the set of all permutations on the numbers 1 through n. We know its size. There's n factorial of them because there's n factorial permutations. We know that we can take any 2 permutations and multiply them together to get another one. So what we say is we say that the set is closed under multiplication. We can multiply 2 objects and get another object in there. The identity permutation is in there, and it has the property that when you multiply it to any other permutation, it doesn't change it. Every one of the permutations has an inverse. That's a permutation that when you multiply it to the one you started with, you get the identity. How inverses and multiplications relate to one another is that the product taking the inverse of a product is taking the inverse of each of the elements of the product in reverse order. Multiplication is associative. Grouping brackets don't matter, in other words. It's not necessarily commutative, so order in which you multiply does matter. And we've got these cancellation properties that tell us we can cancel things off the left-hand side of both expressions or the right-hand side of both expressions. All right, so that summarizes everything we've got so far. And this is what's known as the algebra of permutations. This is permutations and then corresponding multiplications and inverses and an algebra associated with that. So let's go ahead and do a couple more things with this algebra. So let's show that if I have permutations alpha and beta, and I take alpha followed by beta, then alpha inverse, and I get back my permutation beta, then that meant that alpha and beta actually commute with one another. And notice there's two directions here. There's an if and only if. So this is usually, written as like a double-headed arrow. What this means is there's two directions to prove here. There's this direction that says that if alpha beta alpha inverse is beta, then they commute. So what we'll do is we'll suppose alpha beta alpha inverse is equal to beta. Then what we want to do is try to conclude that they commute with one another. And remember, commute means that alpha beta is the same as beta alpha. It doesn't matter which order you multiply them in. You'll get the same result. So how are we going to do that? What I have is alpha beta alpha inverse is beta. I want to show that they commute. So one way to do that is to start with the equation we know. And I see an inverse there on the left-hand side, on the left-hand side, the right part of the left-hand side. So I'm going to multiply by alpha to both sides. You might, in terms of algebra, if you're doing these things and you've got like, x times a half is equal to y, you might say, well, times a half, I'll just move the 2 over to the other side. In some sense, that's what we're doing here, but we're not thinking about it as sort of moving something from a bottom to a top on the other side or cross multiplying. What we're doing is we're thinking about we're multiplying by the inverse to both sides. So I'm multiplying by the inverse of alpha inverse, and the inverse of alpha inverse is alpha. So then that is true. So alpha beta is equal to beta alpha. Now I made a bit of a step there, but the point is that I can regroup using my grouping brackets and get that alpha inverse alpha up here together, which I've replaced with the identity, and then multiplying by the identity leaves things untouched, so I can sort of get rid of it. But there's a few steps sort of involved right there, but that's the main point. And therefore, alpha beta commute. That's what we wanted to prove, is that it doesn't matter which order you multiply them in. On the other hand, suppose alpha beta commute, then what we have is that alpha beta is equal to beta alpha. And from that, I can multiply by alpha inverse to both sides. And again, since inverses exist, just sort of indicate much the way we did it before. And then we get alpha beta alpha inverse is equal to beta, since alpha alpha inverse is the identity, and we use the property of the identity, that when you multiply by it, you leave it unchanged. And that gives our proof. So what this tells us is that if we multiply alpha and its inverse, we sandwich a permutation between alpha and its inverse. The only time it'll have an effect on what's inside is when it doesn't commute with what's inside. It will turn out that this, what seemingly might be a straightforward observation, is the key to understanding how to solve Rubik's Cube. It's moves like this: do something else, undo the first thing you did. And those are essential moves that we're going to uncover on the Rubik's Cube and all the other puzzles. These are essential for solving these kinds of permutation puzzles. In fact, this is essential for dealing with any non-commutative operation. So you may have seen something like alpha, beta, alpha inverse in linear algebra when you looked at similarity or diagonalization of matrices. A, B, A inverse may have cropped up in some places. We called those matrices similar to the matrix in the middle. And that's the same sort of idea here. Whenever you have non-commutative operations, things like alpha, beta, alpha inverse come into play and are really important for understanding sort of big pictures ideas. So that's just a foreshadowing. I'm front loading this. I'm saying like this is really important. But at this point in time, we will uncover it later on, and you will see why it's important and all of that stuff. But for right now, we just noticed that this is related to being able to commute. And so what that means is the only time alpha, beta, alpha inverse is going to be interesting is when alpha and beta don't commute. And that's why we really don't see expressions like this unless we're in linear algebra or a class like this, because everywhere else in our math classes, objects commuted with each other. Right? Multiplication commutes, addition commutes. So everything commutes in our other math classes, which is why we never see stuff like this. It's only important when things don't commute, and that's why it's appearing in this class. Order of a permutation. So this alludes to a question that came up in the chat last day. How do we find the smallest number which, when we raise alpha to that power, gets the identity? Well, that smallest number is what we call the order of the permutation. I like to think of it as, and people refer to this as, the smallest value is going to kill the permutation. So the permutation is mixing stuff up, and if you keep applying it to itself over and over again, it mixes stuff up, you mix them up again, you mix them up again, then the permutation is effectively dead when it's restored everything back to its original spot. And so I want to know what's the smallest value. So for example, in this case, what's the order of this permutation? Yeah, the characteristic of a ring is effectively the value that kills the identity. How many times you have to add the identity to itself before it gets killed. In some sense, this is, it's related in some way to that, but it's more related in terms of a ring. When you have multiple, so in a ring you've got multiplication. So how many times do you have to multiply a number to itself in order to get the identity, or an element to itself to get to the identity? It's also related to how many times you have to add a number to itself to get the identity, and that's the characteristic part. So that would be like the additive, the order under addition, but then there's also an order of an element under multiplication. How many times you have to multiply it to itself to get the identity or the unit of the ring, if there is a unit. So that really only works in the case where you've got a ring with unity. Can you always find absolutely. Is it true that there exists a number n such that p to the n equals p, where p is a permutation for any permutation? That is true. It's not the same value of n for every p, but for a given p, you can always find a power of it which returns back to the original permutation. So let's see what it is in this case. So we've got alpha. I want to know what power is going to kill it. So what I'm going to do is I'm going to power it up. 1, 2, 3, 4, 5. And so what happens here is I got 1 goes to 3, 3 goes to 5. And then I have 2 goes to 2, which goes to 2. 3 goes to 5, which goes to 1. 4 goes to 4, which goes to 4. 5 goes to 1, which goes to 3. So that's squaring. I sort of did it in place. Now I'm going to do the cube. So let's look at it as maybe alpha squared times alpha. 1, 2, 3, 4, 5. 5, 2, 1, 4, 3, 1, 2, 3, 4, 5, and 3, 2, 5, 4, 1. When I do this one, I get 1, 2, 3, 4, 5. 1 goes to 5, which goes to 1. 2 goes to 2, which goes to 2. 3 goes to 1, which goes to 3. 4 to 4, which goes to 4. 5 to 3, which goes to 5, which is the identity. So what we'd say is that the order of alpha is 3. And the question is, must the order of an element exist? Must such a number exist? And the answer is yes. So this comes back to your question about, is there a power which will produce the identity itself? Let me just say, once I know that the order of alpha is the identity, then from that, if I multiply both sides by alpha, oh, sorry, I don't get the identity, I get alpha again. If I multiply both sides by alpha, I get that alpha to the 4th is alpha. So it's equivalent. Is there a power which produces the original permutation, or is there a power which powering it up produces the identity? They're equivalent. They're just going to differ by 1. The smaller number is going to kill it, and then you can bump it up by 1 to get the permutation back again. Why is this true? So we'll finish with this. Why is this true? Well, it's true because Sn is finite. And you might say, well, what does that have to do with it? Well, the idea is if I take alpha and I power it up, alpha squared, alpha cubed, alpha to the 4th, and so on, that I can't get infinitely many different permutations because there's only n factorial permutations of n objects. So there is some k and some L such that those two have to be the same thing. So I can't have infinitely many things happening here. So I'm going to have a repetition at some point. So there's going to be an alpha k, I'm going to have an alpha L, and so on. Not all of these things can be different. There's going to have to be some overlap. So I'm just saying that, well, there has to be 2 things that are equal. In fact, there's a lot of things that are equal, but for sake of argument, there's at least 2 things. So what does that mean? It means that alpha to the k is equal to alpha to the L. In my diagram, I'm assuming L is bigger. So that means that the identity is alpha to the L minus k. And so such a power exists. In other words, the order of alpha would have to be, at worst, it's L minus k, whatever that is. So because of the finiteness, elements have to have orders. And so that means that for every permutation, there is a number which kills it, and the smallest number is what we call the order. And I'm leaving it off there. We will finish this last couple of examples next day, and then we'll get into the cycle form.